So, welcome back to Statistics, Lecture 3. I spent a lot of time on this title slide. A quick reminder of where we were, actually, before this. We did the central limit theorem with many of your responses, thousands of them, 4 of these thousands of this gentleman, but many others from all of you. Your hand must have heard from all the dice rolling. I'm sure you use my physical dice for this. And then this is what you got out. Rolling 1 die gives you a distribution that is flat, and 2 dice gives you a distribution that is triangular, and rolling many dice, 10, that gives you a distribution that is Gaussian, and that is the magic of the central limit theorem. And you've proven it in an experimental kind of way. And before I do this, actually, I have one more thing to do in this context. And let me see whether I can find this. Do I have it here? Very nice. I thought I had this all sorted. 7 responses. I've decided for the rolling dice question, there is one person who got at least 3 out of these responses right, and that person is Mahira. Is Mahira here? Ha! Fantastic! So you deserve actually 2 prizes, one for this and one for asking so many good questions, but I'll only give you one. So thank you very much. So that was a quick intermezzo, and now we continue with our presentation. Because well, we made this connection between errors and uncertainties and Gaussians, and because of the central limit theorem, errors are very often Gaussian, especially in the central bit, and because Gaussians are so important and so frequently used, it's useful to have a look at them, and we found that about 2/3 of events should lie within 1 sigma of a Gaussian, and 95.5% within 2 sigma, and 99.7% within 3 sigma. So that is the state yesterday, and therefore the plot, if these vertical lines represent error bars of plus minus 1 sigma, it means about 2/3 should hit the line if the line describes the data accurately and the errors are sensible, and 1/3 should be about outside. So this is what's the case here. Here this is not the case. This almost certainly means that whoever made this plot completely overestimated their errors. Some people think this is a good thing. They call it conservative. I think it's a bad thing. I think most people who take statistics seriously think it's a bad thing. Do not hide behind your error bars. That would mean, for example, that you would miss if maybe the curve doesn't really describe the data. That would be an interesting result. But if you blow up the errors, you will never see that. So don't blow up the error bars. Be honest with them and calculate them as accurately as you can. And then there is the Flat Earth Society faction in this room, very much like this plot as well. And bless them. Okay, so this is the answer. And this is the end of my short summary. Now we move on, and think about using these kinds of uncertainties, Gaussian confidence limits, in order to discover something. So what kind of discovery do I have in mind? I have in mind the idea that I have a hypothesis. My hypothesis is, say, the standard model is correct, and then I get a measurement that is 3 sigma away from my standard model, and then I can reject the standard model or can I not. So what we've just learned here is that from this plot, from these plots, that 3 sigma away, 99.73% of the events should be within 3 sigma. So to have 3 sigma or more, you always integrate. You don't say exactly 3 sigma away. That means nothing. The probability of that is 0. But 3 sigma or more away, the probability of that is 0.27%. So if I say, say this is a standard model, and I have and I'm 3 sigma away, and I say, okay, I've rejected the standard model, the probability that I make a false claim, because in reality, under the assumption that the standard model is true, the probability that I make a false claim because there's just a fluctuation is 0.27%. So that's actually not that big, and we didn't discuss 1 and 2-sided tails. Your supervisors will tell you that. But we usually don't do that, at least not in particle physics. And in many sciences, actually, they do this, but we do not say that 3 sigma constitutes a discovery. Why not? The chance that I make that the standard model is correct and I get a fluctuation of this size or bigger is really quite small. So why not risk it and say I found evidence that the standard model is false? And the reason is that we always look at many places. In some cases, for example, you might have a histogram full of data, and there's only one histogram bin that deviates by, say, 3 sigma from the expected number of events. But if I look at 100 different bins, the probability that one of them does this becomes actually quite sizable. Let's calculate this. The probability that I get at least, if I have 100 different histogram bins or 100 different experiments, we do clearly more than 100 experiments, right? We do lots of these, 100 different measurements, that at least one of them has a 3 sigma effect. Well, that is 1 minus the probability that none of them have a 3 sigma effect, right? All of them are within 3 sigma, 1 minus that. And that is the probability that one of them is within 3 sigma to the power of 100. I have a computer, I can calculate this, and that is 1 minus 0.76, so it's 24%. Now, the probability of claiming a false discovery of a quarter, that is far too risky. I'm not going to do that. So this is what these p-values are about. In a way, you can interpret the p-values as the probability that, under the assumption there's nothing new, you make a fool of yourself by claiming there is something new. That's what basically the p-values represent. And then you have to take into account whether you looked only at one single place or whether you looked at many different places before you knew discovery. But the more often you roll the die, the more likely you get a specific result, right? The more often you do an experiment or look at something, the more likely you are to get a 3 sigma or 4 sigma effect. It's really important. Because it is important, I calculated a few more values for you. So to have, this is the first one we started off with, we have 1 3 sigma effect and 1 measurement. That is this 1 minus 99.73%, this is 0.27%. And 10, it's 2.7. In 100, it's 24%. And if you do 1,000 measurements, then it's 93%. So you can be guaranteed that somewhere in our field, there's a bogus 3 sigma effect. It's really 3 sigma away, but it doesn't signify anything new, because surely we are doing more than 1,000 measurements in our field, right? There will be one of those. And that's why when we see 3 sigma effects, we don't dismiss it. We say it's an interesting observation, it's interesting, it's a hint, it's an indication, but we don't get overexcited, because the large number of measurements we make implies that you'll see these come and go occasionally. And I find it a bit mind-boggling, because the same result means something quite different when you had, if you look only at one single measurement, one single histogram bin, and he decided that from the start to only look into this one single histogram bin, and you see a 3 sigma variation there, or whether you also looked at the other 99 bins in the histogram, or the other 99 measurements. I find that a bit mind-boggling, so the result that you look at means something different if you look at other things as well. Or, yeah. In particle physics, we usually take 5 sigma as the threshold for discovery. That's of course somewhat arbitrary, but 5 sigma is pretty good, pretty safe. So that having a 5 sigma effect in 100 measurements, the probability of that is tiny. Still. So 5 sigma is a very safe threshold to take. If things are Gaussian, or if they're not, if you have calculated your p-values properly, taking into account that maybe they're not so Gaussian. Any questions about that? Look elsewhere effect, it's called. Super important. Was around a lot during the Higgs discovery times. Local p-value, local significance, and global significance. The global significance was always the one taken into account the elsewhere effect. Yes, please.
So have you ever made a discovery more than 5 sigma?
Yes. You can see more than 5 sigma, but yes, there's the current evidence for the Higgs will be significantly more than 5 sigma by now. The one question we asked, I think in the lecture, in the last lecture, is how meaningful it is to talk about 10 sigma or 20 sigma or something like this. But you can somehow define these things and say I've got an observation that is 10 sigma away from the expectation. And it certainly means that you've observed something, assuming you did all your math and your statistics right, you observed something that's incompatible with the null hypothesis. So it is in that sense meaningful, but whether it makes a difference, whether it's 10 or 20 sigma, I don't know, it probably doesn't make a difference. So I would stop quoting sigmas at some point, or quote them with caution. Okay, so there was that. Now, a blast from the past, we did the central limit theorem. I'm going to give you a second version of the central limit theorem. One derives from the other. And some of you said, I want to do a bit more theory. I'm sorry, I will not, even this derivation, which is actually not that hard, I will not do just to save a bit of time and a bit more room for other topics next time. And that is, but it will behave in a way that you find intuitively appealing, I think. So the central limit theorem, the way I introduced it, referred to the sum of random variables. Quite often you might take the average of some random variables. For example, if you repeat a measurement and you want to measure the same thing again and again and again, then you would usually take the average. And then the expectation value of the average is, of course, the average of the expectation values that you would expect. I think less obvious, and I think that would require some proof if I did this properly, is that the expectation value of the standard deviation is the one that you get from this divided by n. Basically, this division by n just carries through here, but why that is the case is not so obvious, I think, from without proving it to you. So I ask you to just accept it or go home and derive it yourself. And then, if all of these are the same, then when that is the case, when you repeat a measurement, you measure the same thing again and again and again, then all of these are the same and all of these are the same. And then this expression just means n times sigma. Because sigma, sigma, plus sigma, plus sigma, plus sigma, right? N times sigma. And then this is the result. So the uncertainty decreases as I average by square root n. And that is the second miracle of square root n, or the first. Is it the first? It's the first. The first miracle of square root n in this talk. And that means averaging is good for you, but also a case of diminishing returns. In order to halve the error, you need 4 times as much data. And that is one of the reasons why we are under such pressure to increase our luminosity all the time. Imagine that you took, say, 2 years of data, and you have a decent measurement, and you want to improve this measurement significantly. Say we want to halve the uncertainty. That means you need an 8-year measurement, so another 6 years. not many PhD students will stay around for that long. If you want to do it again, you need 16 years. Definitely no PhD student will stay around that long. No, we do more things than just decrease errors of previous measurements with the high luminosity upgrades. But this is one of the things we do, and that's why and that's why the high luminosity, of course, is essential, because then we collect these statistics much faster. So, all right. Now let's use this in practice, because that actually concludes all this thing that I talked about. But we have errors and uncertainties, and in principle we are completely ignorant about them. But now I'm telling you, you basically can know everything about them. Everything-ish, if that exists. We know that under many circumstances at least, the uncertainties will be Gaussian, and now I can estimate this Gaussian, the mean and its width, by repeating my experiment many times. Here I repeated my experiment 100 times, or 101 times for some reason, and and I measure something. I don't know what it is. It doesn't really matter. Maybe it's a counting experiment, and I sometimes measure 20, sometimes 40, but on average I measure 30, and the width of this distribution is 4.6 roughly. Now, in order to get my best estimate of the value I want to measure, is that I take the mean. I take the average of my 101 measurements, and that is my 30. So that's my best guess for the true mean. And that thing has an uncertainty, and that uncertainty is not 4.6. 4.6 is the uncertainty on the individual measurement, and the width of this distribution. That is because the average is 4.6 divided by square root 110. So it's approximately 0.46. Okay? So now we have everything. We know the Gaussian that describes my uncertainties, and I can just put I use this, that is uncertainty on the mean, as the uncertainty divided by square root n. N is 101, so the uncertainty on my mean is 0.46. And this concept of the uncertainty on the mean puzzles some people sometimes, and I understand that, so I'll try to depuzzle it a little bit for you. So what do you mean, the uncertainty on the mean? Imagine that there's one big sample, one true distribution of my data that nobody really knows, but it has infinite entries, and in my experiment I take some number of measurements. In the previous one was 101, here I take 10. And I make a measurement of the mean, and I get also the uncertainty, and I get a measurement on the width of the distribution. I take another measurement, I get another measurement of the mean and the width, etc. So these means, if I put them in a histogram, they will fluctuate a little bit. They do the distribution. And it's the width of this distribution that I mean when I talk about the uncertainty on the mean. So in the previous one, it would be, okay, I took 101 data points. If I repeated this many times, I would get also a jitter on the mean I get. And the width of that jitter, that will be this number. Okay, so that's what I mean with uncertainty on the mean. Any questions on that bit? Because we're changing the topic now. We're changing it to...
By the way, somebody yesterday asked me what was the name of the package that you used to draw the random distribution and then it generates the data points for you. You arbitrarily draw the...
That is a student of mine wrote this for me. The interface is bouquet. So that is the thing that allows you to draw. And and the recent version it stopped drawing properly, so you saw that it sort of stopped drawing, the lines sort of interrupted. So I'm trying to fix that. But it's not a commercially available package. It's a PhD student of mine who did this for me.
Okay.
Well, I'm happy to share the code.
Okay.
I have to.
I have given them some exercises to, let's say, draw, let's say, sign distribution, and then that, of course,
Yeah.
that's in root, but okay,
Yeah.
that seems more.
It's fun. It's fun. Yes, because you can draw anything arbitrary. It's quite cool. Yeah. So, so Daniel Saunders. Remember the name? He's a very bright guy. Daniel Saunders is the guy. Very smart. But also now in industry, programming games and stuff like that. Anyway, so after this, I mean, this is what I wanted. I wanted a little bit of an intermezzo before I change topic. And I'm going to rush through this a little bit just to make sure we have time at the end for the bit that I find important. I'm going to introduce you to two further distributions. So we have the Gaussian, and I hope I convinced you why the Gaussian, and why the Gaussian is so very, very important, and it pops up everywhere. But there are two more that really pop up a lot in particle physics. The first one, that actually is not that frequent, but it's the introduction that we need for the second one, is a binomial. And the idea behind a binomial is you have a fixed number of trials. So you try something out a fixed number of times, so you toss a coin maybe 5 times or something like that. And you have 2 possible outcomes. For a coin, it would be heads or tails. You can also use it for dice, but a die has 6 possible outcomes. You have to reduce it to 2. So you could say, I roll a die 5 times, and I record whether it's an even or odd number, or if it's number 6 or not the number 6. That also is a completely valid way of doing it. Traditionally, they're called success and failure. It's a bit judgmental maybe, but that's what they usually call. And there's many board games where, for example, if 6 is required to progress, then a 6 would be a success and everything else would be a failure. The probability for success in a single try is P. In my example, this board game, where I need a 6, it's 1/6, because I have a 6-sided die. And then the question that this answers is what is the probability to get R successes, and then consequently n minus R failures, when I try n times. So if I roll my die 5 times, how likely am I to get 1, 2, 3, 4, 5, 6s, or 0 6s? And yes, here it says whiteboard. So I will derive this for you, but in order to cut corners a little bit and save a bit of time, I'm just going to give you the answer. And I'm going to talk you through the answer at least a little bit. So if so this is my probability, my binomial, and this is the number of successes, the number of trials, and the probability for success in each trial. And concentrate only on this number now. So if I try R times and I want R successes, the probability of success with 1 try is P, 2 tries and 2 successes is P times P, 3 times and 3 successes is P times P, etc. So that gives me P to the power of R. And then say, okay, after I've had my R successes, I want n minus R failures. The probability of a failure is 1 minus P, and the probability of n minus R failures is then 1 minus P to the power of n minus R. But that would be the case for an ordered outcome. First R successes, then n minus R failures. I don't care in which order I get my 6s and non-6s or whatever. So I have to multiply this by the number of ways there are to pick R things out of n, R successes out of n trials. So basically the number of ways in which I can order these. And that is represented by the symbol, and this means n factorial divided by R factorial and n minus R factorial. So that's it, that's the binomial distribution. Not properly derived, but I hope you find it sensible, at least, and plausible. And this is how it looks like for different values. So I took P as 30%, why not? And I plotted it for different numbers of trials. So for 0 trials, obviously I can't succeed, right? There's no chance. So the probability that I get 0 successes is 100%. And the probability that anything else is 0. For 1 trial, also more or less by definition, the probability to get 1 success is 30%. and one failure, and 0 successes is 70%, that's one failure. And then it moves on a little bit, it becomes a bit more complicated. And this is now for 10 trials, 100. Do you see what's happening there, by the way? What is this turning into? It's turning into a Gaussian, obviously. Like everything does when you add enough data together. So the Poisson, the binomial distribution will become a Gaussian eventually if you have enough trials. And the expectation value is just n times p. That makes sort of sense. If my probability of success is p, then if I try n times, I expect n times p successes on average. And then there's also a standard deviation that has a square root n factor in there. Always lots of square root n's. And one thing I think is sort of nice and plausible about this expression is that it is symmetric in success and failure. Because if I have one success, it means I don't have one failure, and the other way around. So this is the probability of success, this is the probability of failure, it's symmetric in those two. That's binomial, super quick. And this is a situation where the binomial doesn't apply. At the moment, we could probably, if you picked the right moment, just gone outside and had a look actually, looks a bit similar. So this is a flash of lightning, and you could ask the question, if I expect on average, within a certain time span, 5 flashes of lightning, how likely am I to get actually in this particular time span 3 or 4 or 7, etc. And that's the question that the binomial answers, and that's the Poisson answers, and so the number of things that happens, counting things in a continuum. And here I will probably do a little. I'll do the half derivation. So let me look for that. Okay, let's see whether by some miracle, I haven't started this yet, this will work straight away. Usually it's a little bit reluctant, but that looks quite promising. That looks promising here, but not there. Okay, so
Jonas, you have just 2 minutes.
what?
2 minutes.
So 2 minutes for the entire thing? Seriously?
Yes, because John Ellis is just waiting for us.
Oh, right. Under these circumstances, what we'll do? What will we do under these circumstances? I think we wrap up and we'll do this later. I will just simply go to this slide and only do this. Where's my summary slide? Give me a second. I'm going to go to the summary slide. All will be good. That's what I wanted to do. All these beautiful things. Okay, so what we've done today is much less than I thought I would do. We have done the central limit theorem for averages, we have done the binomial distribution, and we haven't done the Poisson distribution. And maybe we won't do it ever. And we will maybe do very quickly on Friday, and we will do chi-square fits on Friday, and we will do likelihood fits on Friday. And we will do Monte Carlo simulations on Friday. These are the 3 things we will have time for if we start on time on Friday, which I will aim to do. And that is it. And John Ellis is next, but if there's a minute for questions, then I'm very happy to take them.
Yeah.
One way would be, I mean, these are very interesting lectures. So these topics, maybe we have an extra time slot sometime. Maybe after.
I would certainly be able to fill it. That's no problem. I have material, as you can see. So yes, if the students want it, and if you guys are happy with it, I'm very happy. I have a lot to say.
I would be very interested that you just covered these topics. I was learning, I'm so glad. That's for very interesting. The discussion is not going to be cut off, but I think we should find even before Friday some time slot, even if it is after 3:30, to cover this.
Yeah. This is one.
I don't mind if it, even if it is in evening, so they could work.
Let's see, we can give a try. Let's see, we can give a try. If there are any questions, let's.
I'm sorry, I just saw his arm.
What's the significance of the uncertainty on me? Where do we use it?
Of the uncertainty.
Of the uncertainty on me.
You use that when you take a measurement multiple times, which I recommend you do, and then you take the mean, and you want to know the uncertainty on that value that you measure. That's it. The significance of that is that it gives you, it gives you the typical deviation of that value from its true value, in some sense.
So sometimes we also are required, or people ask us to quote an uncertainty on sigma itself, so that means uncertainty on uncertainty.
Yeah, I'm not a great fan of that. I think it depends on the context. If you want to, if your result is the sigma itself, say the width of a Gaussian, you want to know the detector resolution, and that sigma, there an uncertainty makes sense. But an uncertainty on the uncertainty most of the time doesn't make sense. And if I get that extra lecture, I think I can maybe make an argument why I don't think that makes a lot of sense, actually.
Okay, thank you.
Thank you very much. Of course, we will try to find another slot for you. Thank you.